Good afternoon and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. I appear wide. This is not what I see on my OBS. Well, we're gonna have to figure out. I think we're just gonna go with it. If somebody has any idea what's going on there, let me know, because it doesn't appear that my output is messed up. Yup. Alright, well anyway. We are going to do a bit of math today. We had somebody come in to another stream yesterday and said that they were having problems with this particular one. I was right, it was on Talos' stream. Yeah, Talos already answered this, but whatever, it's cool. So the method here that we're looking at is undetermined coefficients. So we look at this and say the homogeneous solution for this is going to be determined by saying, okay, what would happen if 2y prime plus y were equal to 0? And the homogeneous solution, or at least the purpose of the homogeneous solution, is to say, like, what is the kind of steady state of this particular system? So if this were a system involving like spring masses or stuff like that, this is not, by the way, but if it were, how exactly would the system behave if you just left it alone and, like, you know, didn't put a motor on it or anything like that? How would it behave if you just did something? So in this particular case, our homogeneous solution, which the person in question already had the homogeneous solution, it wasn't a problem, but nonetheless, still going to look at it. In this particular case, we could actually do separation of variables, just because, well, this has no other system attached to it. It is a first order linear differential equation. So with that, we can, you know what, we don't even need to do that. That's all right. If we assume that y is equal to some e to the rt, then y prime is going to be equal to r times e to the rt. And the reason we do this is we say, well, look, we're going to have some number that when you derive this thing, it's going to be combined with its original, and those two things are going to combine to get you 0. So probably the derivative and the original function are very closely related to each other. And so in this case, we're going, all right, e to the rt sounds reasonable. So if we do this, we can say we have the homogeneous solution is going to look like e to the rt, and then what would we get? This is 2 r e to the rt plus e to the rt is equal to 0. E to the rt can factor out. That leaves us with 2r plus 1. And e to the rt can't be 0 itself, so therefore it can be divided. Or the whole thing can be divided by e to the rt. Right, since this is never 0. Which leaves us with 2r plus 1 is equal to 0. So, at least one of the things that's here must be 0. So therefore it's going to be 2r plus 1. So this means that r is going to be a negative 1/2. And therefore our homogeneous solution is going to be that we get e to the negative t over 2 or negative 1/2 t, or however you want to do it. It's all good. Okay, and then to get our particular solution, what we're going to do is say, well, let's take that, and we know that just plugging in e to the negative t over 2 is going to get us 0 no matter what happens. So this is why it's a homogeneous solution. It's just the function which will always get us 0 if we plug it in for y, for this system, for this differential equation. So now we want to find one that's going to get us the stuff on the other side. So over here we have 5t sine t. And there's a few ways that you can do this, but generally speaking, if we have a function and its derivative, and it's getting us something with a trig function in it, a sine, then either this must be a sine of t, or it must be a cosine of t. Somewhere in there, either we've got a sine or a cosine. Or both. Stuff could cancel out. Okay, and then we say, well, hang on, that's not it. There's a t in front of it. So in order to get a t sine of t, most likely what's going to happen is that either we've got a t cosine of t that we're taking the derivative of, which will come out with a t sine of t term, or it's a t sine of t term that's just in the y position. So since we don't know which one it is, we have to assume that it could be either. So here we say that this is going to be a times t plus b times the sine of t. Of course. There we go. Or it could have some term which could have, again, ct plus d cosine of t. And again, other terms that we don't see there could just be dividing out or adding or subtracting out with other terms. So we have to take into consideration both of the possibilities. We don't know exactly which one it's going to be, but could happen. Again, some b sine of t could be the original function, and d cosine of t could be the derivative function. Or there's a whole bunch of stuff, like the at sine of t. If we take its derivative, one part of that is going to be a sine of t, which could very well add up and get rid of the b sine of t. We don't know. So we have to consider all possible options. Here we're going to say that this is y prime of y prime particular is going to be, or y particular prime, if you want to put that p closer in there. We take the derivative of the first part, we just get a times the second part is just sine of t, plus, if we leave the first term alone, it's at plus b times the cosine of t. Plus, if we take the derivative of the first part, this is going to be c cosine of t. And if we take the derivative of the cosine part, this is going to be a minus parentheses ct plus d sine of t. So we have all of these possibilities floating around here. We don't know which one it is, but we do know that when we plug both of these things back into the original equation, we're going to get equal to 5t sine of t. Okay, so this was 2 times y prime. Yep. So a sine of t plus parentheses at plus b cosine of t plus c cosine of t minus parentheses ct plus d sine of t. Okay. Plus the original at plus b sine of t plus ct plus d cosine of t has to be equal to 5t sine of t. Okay. So now we have to combine all these little bits and see what we get when we move things around a bit. Okay, so here we get nope. I hit that one instead of the actual pen. Cool. 2a sine of t plus 2at plus 2b cosine of t plus c cosine of t 2c. Man. Minus ct minus d. We'll just keep the parentheses here. That's twice that. Sine of t plus at plus b sine of t plus ct plus d cosine of t is equal to 5t sine of t. Okay. Now if we organize things together, what we're going to see is that all of our sine of t's can come together to get us, let's see, we can, 2a minus 2ct minus 2d plus at plus b is all sine of t. And then cosine of t is going to be 2at plus 2b plus 2c plus ct plus d cosine of t. Now, we can separate out these two equations, or we can separate out the two parts into two separate equations, which a lot of people get really bothered by. So if that's you, don't worry, I did too. But what we're doing here is we're saying, okay, if we have a whole bunch of stuff that's then multiplied by sine of t, in order to make this actually equivalent and not just look for an intersection point, which again is possible but not particularly helpful, we want these things to be literally equivalent. So in order to get on the left-hand side 5t sine of t, on the right-hand side, or in order to get on the right-hand side 5t sine of t, we'd have to have literally the same thing on the left. And here, in this particular case, we're going to look at this and say, okay, well, that's only ever going to happen if our negative 2c and a here are going to sum up to 5. So we're going to need, again, negative 2ct plus at has to be equal to 5t. And then 2a minus 2d plus b has to be equal to, well, we get here a plus 0 sine of t. Our other coefficient is going to be 0. So this is going to create two equations. Then on the cosine side, we don't have anything on the right. So this is going to be a 0 cosine of t. You don't have to do that necessarily. I just like the bookkeeping to make sure everything's going to be the same. So here we've got a 2at and a ct, which are going to sum to 0, and also a 2b, 2c, and d, which are going to sum to 0. So taking those all together, we've got a negative 2c plus a is equal to 5, because again, this is our t sine of t equation. We've got a 2a minus 2d plus b is equal to 0 is our sine of t constant equation. We can get a 2a plus c is going to be equal to 0 as our t cosine of t equation. And also a 2b plus 2c plus d equals 0 as our cosine of t equation. So this can actually split up into 4 separate equations, and we have only 4 unknowns, so this is now solvable. Backslashes, that's what problem. So let me take a picture of this. Send this one over to the person in question if they are not here. Okay. So we're going to take these and set it up as a system of equations. So here we have a minus 2c is equal to 5. 2a plus b minus 2d is equal to 0. 2a plus c is equal to 0. And 2b plus 2c plus d is equal to 0. And then stack them up. Cool. So if you're solving this by hand, the obvious place to start is right here, because you have a 2x2 system of equations. You can solve for a and c immediately. Done. Once you do that, then you'll have a 2x2 system with only b and d, because a and c will have numerical values. You can plug those in, drag them to the other side. That's actually pretty easy. Nice. Right, so this is like the obvious way to do it, in terms of trying to do a 4x4 system of equations it breaks nicely into two separate 2x2 systems of equations, which you do need to solve sequentially due to the fact that, again, equations 2 and 4 are still part of a 4x4 system of equations. So you just got to wait until you solve the other two, equations 1 and 3, since they form a 2x2 system of equations. Now, if you wanted to, this is also a way to get into some linear algebra, and you could say, okay, I'm going to take this as coefficients 1, 0, -2, 0, and move over. Cool. And 5, that's not helpful. Looked good for a second there. 2, 1, 0, -2, 0. 2, 0, 1, 0, 0, and 0, 2, 2, 1, 0. So from here, we have a linear system of equations. It is, again, 4x4, and this is what's called an augmented matrix. And really, the way that it's built right now is that we have our whole 1, 0, -2, 0, 2, 1, 0, -2, 2, 0, 1, 0, and 0, 2, 2, 1 is the coefficient matrix multiplied by a vector ABCD. If you remember how you multiply matrices, this is going to take the first row and say, I'm going to multiply my first row by my first column. This is going to be A times 1 plus B times 0 times -2 times plus -2 times C plus 0 times D. And that gets us what we see back in the previous spot here. This is plus 0b minus 2c plus 0d. Right, that's what we see in here as well. And likewise for the other three. The exact same thing works. So the way to actually solve this matrix and be able to figure out what it is that we want to get would be to say, okay, I want to take all of my terms that are beneath my initial 1, and I want all of these other ones to be 0. So I need to add the equations together in some way, shape, or form. If we're just blindly doing this, again, without worrying about the stuff we had over on the left with you know, a 2x2 system of equations leading to a 4x4 solution, what we can do right now is just say, okay, I want to then take equation 2 and add to it -2 times equation 1, or row 1. Similarly, I'm going to add to this one a -2 times R1 as well. That will get rid of all of the first terms all the way down. Our goal here, oops, sorry, this is equal to, we had 5, 0, 0, 0. Our goal is that we need what's called the identity matrix multiplied by our vector ABCD to be equal to whatever solutions we're going to get for those four values. Now the identity matrix in this particular case is going to be 4x4, and so that is going to look like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. right? We could do this by row operation. So we take the individual operations that we're doing, we're saying, okay, we're going to multiply, keep row 1 exactly as it is. We don't care about anything. We don't want to move anything yet. Just leave it as is. So 1, 0, -2, 0, augmented with 5. On the next row, we have -2 times the row above it, and add to whatever we have. So this is going to be -2 plus 2 is 0. 0 plus 1 is going to be 1. -2 times -2 is 4, plus 0 is going to get us 4. And 0 plus -2 is going to get us -2. And -10 on the top plus 0 is going to get us -10. All right, repeat for the third row. So now -2 plus 2 is going to be 0. 0 plus 0 is going to be 0. That's nice. -2 times -2 is 4, plus 1 is going to be 5. 0 plus 0 is 0. And -10 plus 0 is going to be -10. And wouldn't you know it, we now have something that we can solve directly. So row 3 is solved. We just need to now multiply the value that's here. So multiply row 3 by a 1/5. I like to talk about this specifically in terms of just addition with other rows and multiplication of a particular number. To say that we're, dividing the row by 5, like, sure, I guess, but if we simply talk about like linear combinations of all of this stuff, then it ends up making it a little bit nicer to talk about. So I could, in fact, say this is row 3, this is row 2, this is getting stored back to row 2, this is getting stored back to row 3. That's like the longhand version of it. This is row 3 multiplied by 1/5 is going to get stored back into row 3. Okay. Fourth line we didn't touch, so 0, 2, 2, 1, 0. All right, so now we repeat the row operations, this time for our second position. So here we want to get rid of, well, there's nothing here, so we just need to get rid of that last one. So this is going to say take row 4 and add -2 times row 2. And I guess we could also get rid of row 1 with this one. The fraction's a little bit wonky just because, but it's not like it's bad. It's not hard. It's just like you might not like fractions. So you can wait around in order to do something, which will be a bit nicer. Or we could just do it now. So I don't really care, but we'll just wait around. So here we get 1, 0, -2, 0, augmented 5. 0, 1, 4, -2. Again, same thing. We could have also gotten rid of the things above and below 5, but we'll just wait. -10. Okay, row 3. So 0, and we're adding stuff from... No, we're just multiplying straight across. So 0, 0, 1, 0. -10 times 1/5 is going to be -2. Next one, 0. All right, -2 times row 2. So -2 times 1 is -2, plus 2 is 0 by design. And then we say -2 times 4 is -8, plus 2 is -6. Nice. -2 times -2 is 4, plus 1 is 5. And then -2 times -10 is going to be positive 20, plus 0 is positive 20. Alright, so again, we know that C was going to be -2. Okay, now by adding in all the rest of the stuff, we can now pivot on that particular value and knock out all the rest of this. So this is going to be row 1 plus 2 row 3 put back into row 1. This was put back into row 4. This was row 2 plus a -4 row 3 put back into row 2. Row 3, leave it. Row 4. Turkey vulture just flew over, cast a huge shadow. Plus 6 row 3 put back into row 4. Alright, 1, 0. This is the only thing that's going to change, or everything beyond this point is going to change. There's nothing in the first 2 columns that's going to do anything. So, leave those as is. We said this is going to be twice row 3. Add to -2 becomes 0. And again, our 4th column here doesn't have anything in it, so that's not going to change. It's also a 0. And last column, our augmented column, is a -2 times 2. Yep, it's going to be -4 plus 5 is going to be 1. Okay, second row, we get a 0 and a 1. And then we said -4 times row 3 plus 4 is going to be 0 here. 0 times -4 just leaves us with what we started, -2. And then at the last column we have -2 times -4 is going to be +8 plus -10 is going to be a -2. Okay. 0, 0, 1, 0, -2. And then lastly, 0, 0. This is also going to be a 0. We needed 6 of row 3 plus -6 gets a 0. 0 of the zeros here. So, or 6 times 0, it's just going to be 0. And that leaves us with the 5 that was underneath. And then 6 times -2 is -12, plus 20 is going to be +8. Oh. We get a fraction. It's not too bad, I guess. We got all the rest of the stuff cleared out, so this isn't too bad. And good morning, afternoon, evening, wherever you are. And hello, my name is Obi-Wan Pez. This is N-Simplex Pachinko. We do all sorts of mathy type stuff, typically on Tuesday nights, but my next couple of weeks are going to be all messed up because I'm moving. So I'm going to stream when I can. Alright, at this point, we need to take row 4. If you have any questions, do let me know, and I will attempt to answer anything you got. Put that back into row 4, and we're going to take row 2 and add to it. This is going to be 2/5 of row 4, and put that back into row 2. Nice. What's your current level of expertise? Ah, gotcha. Yep, that's also helpful. Alright, so 1, 0, 0, 0, and 1. 0, 1, 0, 0. This is going to be, so we take row 2, add 2/5 of row 4, so 2/5 of 5 is going to be 2. Added to 2, we get a 0, so that clears that up. Again, by design. And then we come over here and we say this is going to be 2/5 of 8, is going to be 16/5 minus the 2 that we had to begin with, which is 10 fifths, negative 10 fifths. So 16 minus 10 gets us 6 fifths as that number there. Well, that's true. And it all kind of depends on where you are. So I have had college students who were at like what we would probably be teaching to middle schoolers. So basic algebra. And then we have other classes where we've been teaching, differential equations, which is what I started this thing with, way up there, to high school students. So there's an array. There's quite a large range of students. I guess also, depending on where you're from, like the differences in the curriculum may be pretty significant. I know we're moving to the UK, so my children will be learning like English, the English math curriculum, which is a lot less of the separation that we do in the United States, where we have like algebra, geometry, algebra 2, trigonometry as kind of your 4 years as a typical high school student. In Maryland, where I'm currently staying, it's more algebra is going to be in 8th grade, is pretty typical. And then 9th grade is going to be geometry, 10th grade is algebra 2, 11th grade is trigonometry, and then 12th grade is like pre-calculus, functions in trig, maybe calculus, kind of depends on where you're going. Or a lot of students will do statistics and or like kind of life sciences math, where they learn a bunch of like, here's some statistics, here's some probability, here's some, algebra type stuff, and then you just kind of see how things go. In England, it's a lot more like, here are some problems we think are within your grasp, try and solve them. And then when they solve those, they're like, here are some more problems that we think are within your grasp. Calculate truncated pyramids. Yep, okay. So you're looking at a frustrum. So typically it'll be either a cone or a pyramidal type shape, and then those don't connect. Something like that. That's behind my head. Yep. So that's the word we use for it. Frustrum. Many of my students find it frustrating, but all right. So here we have A is going to be equal to 1, B is going to be equal to 6 fifths, C is going to be equal to negative 2, and D is going to be equal to 8 fifths. Okay, so with that, this is differential equations, but at the moment I'm using linear algebra to solve it. So what we did was we ended up with I forgot something, didn't I? Yeah, I did. Haha. That's what I forgot. Homogeneous solution is going to be a linear combination of that thing. There we go. Okay, we'll come back to that in a minute. Anyway. So we were looking at differential equations. If you've done any like sort of stuff with calculus or even just heard of calculus, this is kind of helpful to see what it is that we're talking about. So what we're doing is we're taking a function that we call y, which may be f of t or something like that, but we're just shorthanding this as y. And we're saying that when you add it to 2 times its derivative, which, again, if you're not sure what that is, that's all right. Derivative of a function is basically what is the function that constitutes its slope at all individual points. So if y equals 4 times t, this is a linear function, and y prime would be equal to its slope. Well, its slope will always be 4, because as we go along the function itself, it just always has this constant slope. That's pretty nice. If y were equal to t squared, what we do is we look at the individual slopes that are going along this parabola shape. And the slopes for all of these things end up being twice whatever position we're at. Nice. Yeah, well, welcome and thank you for the follow. Yeah, so the slope of that parabola will be dependent upon the location that you're at. Over on the left-hand side, you're going to get negative slopes, and then as we go further and further toward the middle, our slope begins to shallow out until we hit 0 at its vertex, right at the vertex. And then when we start moving this way, our slope increases more and more. Turns out that the slope of the function y equals t squared is going to be y prime is equal to 2t, twice the distance that you are away in the horizontal direction. So you go over 1, the slope's going to be 2. You go over 2, the slope's going to be 4. And then it just keeps going like that. It's all very nice. So here we were saying, well, what kind of function are we going to get such that what kind of function are we going to get such that if we were to just let the system exist without touching it, that system by itself is going to sum up to 0. So this is oftentimes what we do with, like, if you remember playing with springs that have like weights on the end, right? They kind of bounce around like this a little bit, and then you can actually figure out what the equation is that determines its position and its velocity and its acceleration and all this stuff. It's really cool. This one is not quite that, but we'll let that go. So what happens is we look at this and say, okay, the default of this system is called the homogeneous solution. It's when the regular part of the system is set equal to 0. And we said that, well, if we have a function and its derivative which can be added together which get us 0, then it's got to look something like this exponential function. If you don't know what that is, if you're not sure about the structure of all of it, don't worry about it. Not a big deal. If you have a passing familiarity with the types of functions that we're talking about, then awesome. So here we have something that looks like this function. Its derivative is going to look like this. Better yet, Shark, how's it going? And so we solve the equation and get that here we're going to get the homogeneous equation that looks like c times, just some constant times, e to the negative t over 2. Okay, then we go in and we say, now if we put a motor on this system, which has then a like functional part to it, which basically, like, the velocity of this whole thing looks like 5t sine of t, then this is going to change some stuff. we're not going to have this e to the negative t over 2 thing. We're going to have something that looks like either a sine function or a cosine function. And given that we have a derivative of it, right, y prime, then we'd better have a t that's also attached with it, because it could be part of this function, and we don't know where. This is where the algebra gets a little complicated. Again, if you're not here yet, don't worry about it. But essentially, we take this thing, we plug it back to the original equation, and we get a system of equations which look like this. Stuff that has t sine of t, stuff that has sine of t, stuff that has t cosine of t, and stuff that has cosine of t. And we know from above how much stuff we need. We need a 5 t sine of t and nothing else. So we come in and we say, okay, all the stuff that represented t sine of t was equal to 5, and these are the coefficients that belong to it. All the rest of the coefficient sets have to be equal to 0. When we move all the way down, we do this linear algebra to try and solve the system of equations a little bit faster. So we can throw all this stuff into a system of equations, and it eventually works down to here. A is 1, B is 6/5, C is -2, D is 8/5. So, because of that, now we take this and we say, okay, climb back up to the top here. Our original solution that we were going to get here, that work? Yeah, cool. Good enough. Right, A equals, shoot. Took too long, now I don't remember what it is. A is 1, B is 6/5. C was -2. Yep, and then 8/5. Okay, so with all of that, now we know that our solution, y, to the original differential equation is going to look like the y homogeneous part plus y times the particular part. So y is equal to c times e to the negative t over 2 plus, this is now going to be t plus 6/5 sine of t plus -2t plus 8/5 cosine of t. But wait, there's more. Alright, there was one last little bit that I didn't actually put on this screen yet, which was there are 2 initial conditions. So initial condition 1 was that at t equals 0, we should get 0, I think. Hang on. Yes. And at oh no. That wasn't given. Nope, sorry. That was the other person plugging stuff in and saying that at 0 all of our sines are going to get 0, and at pi over 2 all of our cosines are going to get 0. Okay. So without any further information, I think this is going to be it. Right. So I don't actually have initial conditions that I'm aware of. So this is our solution. And if you want to know what it looks like, we can also go over to Desmos and say, all right, if we have, y equals, this is going to be c times e raised to the negative t over 2, we need a slider for c. Right, this is the exponential form of this equation, plus this was going to be a t plus 5, 6 sine of t plus negative 2t plus 8/5 cosine of t. All right, so the original behavior of this thing, right? Again, if we don't put like a motor on it or whatever it is that we're doing, this is what it looks like. It's an exponentially decreasing function that goes like that. And this is only when c is equal to 1. If we want to increase it, then it's going to get steeper. If we want to decrease it, it'll get shallower or potentially go negative. All right, let's leave it at like 0.3. All right, if we add in the cosine and sine bits, this causes it to fluctuate, and also the t parts are causing it to go up or down at certain amounts. So if we look at this, we're getting all sorts of crazy stuff going on. Right, and this is a divergent system. It is going to keep growing and growing and growing, and it looks approximately linear in its growth, both toward the upper and lower sides, because if we look at the sine and cosine parts, right, they each have a linear portion in it. So, looking all right. And if we increase this value, the exponential part of it gets more, affects the solution more, but that's only on the positive, or sorry, on the negative side, because all the values over there have e to the negative t over 2 being fairly large. When you start decreasing, or when you start increasing your t value to the positive side, now e to the negative t becomes practically 0 very quickly. And so it's just 0 plus our sine and cosine bits, or, approximately 0. And then likewise, if we had this be actually 0, it doesn't move, it just starts oscillating in the opposite direction. If we have the exponential thing, exponentials always win eventually. So this is just going to come down like that. We get this cool thing. So it depends on what the value of c is as far as what the actual behavior is of this whole function. But overall, once you start getting toward the part where e becomes practically 0, then our sine and cosine take over, it becomes oscillatory behavior, and we get growth as a linear function. And if we wanted to, we should be able to say y equals x, looks like that, 2. Huh. Yeah, it's just slightly steeper than that. But 2.5 is too much. That's fun. We could try to figure this out. So if we wanted to, we could take all of the peaks and find out what their values are. This would be another, just another thing we could try out. Damn it. 19.01. Oh, 2 zeros in both of those, but whatever, it's close enough. 15.268 by 33.038. Depending on how accurate we wanted this to be, right? 46.668 by 103.28. If we wanted to, we could just say, all right, let this be y1, approximate it as a linear function, ax1 plus b. Bam. All right, r squared is 1, so it is as close to linear as we're going to get it. And this is 2.23736 x plus negative 1.13172. So, not too bad overall. If we do y equals negative of y1, does that? Nope. So f of x is equal to? No. It does not want me to do that. F equals? Nope. It's just saying leave me alone. But if we went like y equals ax plus b, that would at least get us the actual line that's in there. And then I'm wondering if I can make this just negative of everything. Does that give us the lower ones? It's at the very least close enough that it's not going to matter. So that's the line that crosses through this point, 0.506, comma 0. I'm trying to see if there's like a significance with that particular number. I'm not seeing one. I don't think it is, but yeah, right. So these are tiny differences. Overall, okay, r squared is not actually 1. It's just really, really, really close to 1. So r squared gets us an idea of how close this value is. All right. Alrighty. If anybody has any other questions about math, please let me know. We'll be happy to work that out. I technically used to be a math teacher for about 15 years at a local community college. And I decided to leave because my family is planning on moving to the UK in about 2 weeks. So we're sending all of our stuff to all of the random people out there who are going to help us move across the Atlantic Ocean and head over to the UK. It's fine. Everything's fine. We're just starting to get all sorts of panicked. Not panicked, but, you know, everything's busy. So it's just kind of like, There's so much going on. We need to do everything like now. That's interesting. I just popped up Heroic Games Launcher on Epic because I was told that Daggerfall is going to be... Elder Scrolls 2 Daggerfall is going to be free right now. And I found a game called Nuclear Fission Simulator. That sounds fun. Oh, interesting. Okay. Alright, anyway. So yeah, I've been working as a teacher for 15 years in mathematics. I've been teaching everything. I've sort of said this before. Been teaching pretty much everything from like algebra, basic algebra, all the way through differential equations. Haven't actually taught differential equations, or sorry, haven't taught linear algebra or multivariate calculus, but like I know them well enough that most of the time, because I've taught differential equations, I've used them so much that I've picked up a lot of it. So it's yeah, it's been a lot of fun. There's all sorts of cool stuff. Let's see, what else? There is actually one other way that I wanted to look at it. there is actually something else that I wanted to do, which was to use... You could actually use... Or sorry, you could actually solve this differential equation here as a first-order linear differential equation. And so no breaking into homogeneous and particular is necessary. I think it's more fun that way, and I tend to get better answers. But it's not strictly necessary. So if we were to look at this, we could say, all right, I want my function here to be that, let's see, we do you multiply on a integration factor to make this work. So we can make this thing look like it is it is a product rule. So if we make this look like it's a product rule, we could say, all right, I'm going to divide through by 2 and make it y prime plus a half y is equal to 5 halves t sine of t. And what we do is we say, okay, the integration factor for this thing is going to be e raised to the, in this case, you take the function that is on the linear term here, and you say that this is going to be the integral of 1/2 dt. Now that seems insane, but eventually it works out, so you could figure out what it is. So you get y prime plus 1/2, oops, this is e to the 1/2 t multiplied by y prime plus 1/2 e to the 1/2 t times y is equal to 5 halves e to the 1/2 t times the sine of t. Over on the left, this becomes the derivative of, this is a product rule, this is the derivative of y times e to the 1/2 t prime is equal to 5 halves t e to the 1/2 t sine of t, and now we have to integrate both sides. Now, I don't know about you, this is doable, it's doable, but I'm not sure I want to do it. Right, the problem here is that the left-hand side just becomes y times e to the 1/2 t, no problem. And yeah, plus c, if you want to stick that on there, that's fine. Okay, but the right-hand side is now going to be this integral, which you're going to have to do integration by parts. And, like, that's going to get pretty gross pretty quickly. I'm not sure that this is going to be doable. Like, it's sort of doable. And maybe this is just the grumpy old man in me that's starting to come out, but yeah, like I don't feel like doing that. So the thing that you'd want to select as your u, which is the thing you're going to derive, is going to be t. Your dv, which is the thing you're going to integrate, is going to be e to the 1/2 t times the sine of t. dt, which is nasty. All right, du then is just dt, and v is going to be the integral of that thing. Which you need to do integration by parts. Okay, the u for this one, the thing that I want to derive is probably going to be the sine of t, and dv, the thing I want to integrate, is going to be e to the 1/2 t dt. V then is going to be the integral of this, which is going to be, when you derive it, you get a 1/2 down, so now we need to integrate, so we need a 1/2 out front. So we take a 2 over 2, feed the 1/2 up, and then the 2 remains outside. So 2 e to the 1/2 t. And du is going to be cosine of t. So that says that our original is now going to be uv, 2e 1/2 t times sine of t, minus integral of v du, which is 2e to the 1/2 t cosine t dt. All right, and then that, we need to do integration by parts. So good news, this isn't like challenging, but it's just kind of onerous at this point because we're like plodding through this thing. We have to just keep doing another integration by parts and another integration by parts. It gets really nasty, but it might actually work. I mean, it will work, but... So here, our u, we have to do the same thing that we did before. So this is going to be the cosine of t. Du is going to be negative sine of t dt. Dv is going to be the other bit, so e to the 1/2 t dt. And yeah, we can stick the 2 in there just so that it's not like we don't forget about it. And then v is going to be same thing here. It's going to be another 2 factor is going to come out front, so we get a 4 e to the 1/2 t. So that particular one is now going to be uv, 4 e to the 1/2 t times cosine of t, minus integral of v du, which is 4 e to the 1/2 t times v du, negative sine t dt. The negative is going to come out front and make that a positive. Okay. So, where does that put us? So, all of this was inside of now a minus sign, which had 2e to the 1/2 t sine of t, which then all of that was equal to that one there. So 1/2 t sine of t dt integral. Oops. Gold! How's it going? E to the 1/2 t sine of t dt was the original thing we were trying to look for in the first place, which, granted, we still have a long way to go here. All right, we just, give us a minute. We're almost there. We didn't know what this particular integral was going to be, so we had to break this down into integration by parts, do it twice, and now we've got another integral in here. which has the same stuff as the first one we were trying to solve in the first place. No worries. I am the grumpy old man, yes. Okay, so here, this is going to be a negative 4 times the original integral. And then this is the original integral. So we can add 4 of said integrals to both sides and end up with 5 integral e to the 1/2 t sine of t dt is equal to, and now all the rest of that stuff. It's going to be 2 e to the 1/2 t sine of t minus 4e to the 1/2 t cosine of t, divide by 5. This is going to be 2/5. This is going to be 4/5, negative 4/5. All right, divide by 5. Get rid of that. And then all of that comes back over to here. And we said, okay, we were trying to figure all this stuff out in the first place. So that's our v now. All of this stuff is our v from before. Yes, I mean, that is honestly true. Using it as e to the it minus e to the negative it, all divided by 2, may have been a better option, especially since there's already another part in there with the 1/2 t. We are assuming that students do not have complex analysis yet. So, yeah, we could just say, well, it's a constant, but at the same time, they might be like, whoa, hey, that's complex. I can't do that integral. Okay, so then that's right, this stuff is equal to 5/2 times uv. So this was t times the v we just found. Better be right. It's probably not right. No. Okay, we got the 5/2 here. That's good. Okay, might be right. Right. 2/5 e to the 1/2 t sine of t. That was a 2/5 e to that minus 4/5 e to the 1/2 t cosine of t. Okay, so that's uv minus, right, still inside this 5/2, minus v, which was, again, this thing we just found, integral. E to the 1/2 t sine of t minus 4/5 e to the 1/2 t cosine of t dt. du, right, which is just dt. Alright, that closes that set of brackets, and then we have to look at, oh no, we have to do more integrals of these things, but we already did them, right, they're here. So we don't have to worry too hard about it. Let's see, e to the 1/2 t cosine of t dt is going to be Factor out a 2, we just get 2 e to the 1/2 t cosine of t plus, nope, sorry, minus, sorry, that's a plus. Plus, man, integral of 4e to the 1/2 t sine of t dt. Which, by the way, we have part of that here, so like we might be able to partially cancel it out, or we can then work our way back through this and say, oh, I know how to find that one because it's this one, and we just do the thing. Right, the sine integral is here, so we can figure it out from there. Okay, so this is going to be... In what order do I want to really screw this up? This is going to be t e to the 1/2 t sine of t minus 2 e to the 1/2 t cosine of t. And if we notice, right, this is working out so far, t and a negative 2t are going to... Yep, sorry, t came in. Alright, those are both there, so that's good. We multiply in the 5/2, and that clears out the, again, 2/5 and negative 4/5 to get us just a positive 1, negative 2 in those particular places. This is also going to be a minus parentheses. So our e to the 1/2 t sine of t was here. That's just going to be 2/5 e to the 1/2 t sine of t minus 4/5 e to the 1/2 t cosine of t. It's fine, it's not going to get all messed up, it's fine. Alright, and then the cosine derivative ends up being cosine derivative, alright, is a negative 2 times that, so it's, I mean, literally all that. So it's just going to be this thing, which then this one we could subtract, substitute it. Okay, so that's going to be a plus. Sign errors are going to get me here. Okay, let's do minus, and then we can literally just write what's up there. Or over there. Whatever direction it's in. Okay. With the 2/5 coming in, or 5/2 coming in, this is what we literally have. So it's going to be minus here is going to get carried through. So we should get a minus 4 e to the 1/2 t cosine t minus 4 times the integral e to the 1/2 t sine of t dt, which we already know from above is, again, this thing. So all that's going to get replugged in to this last term here. Now you see why I like the linear algebra version better. Okay, so again, this is y times e to the 1/2 t plus c is going to be somewhere. It doesn't matter where I put it. Probably should be on the other side, but it's fine. So t e to the 1/2 t sine of t minus 2t e to the 1/2 t cosine of t minus 2/5 e to the 1/2 t sine of t minus 4/5 e to the 1/2 t cosine of t plus 4e to the 1/2 t cosine of t plus 4 parentheses, that thing we just did, 2/5 e to the 1/2 t sine of t minus 4/5 e to the 1/2 t cosine of t. Right. So those are going to combine with the things we just had up here and that one, which are all constants, and they all have fifths in them in some way, shape, or form. So that's pretty cool. So t e to the 1/2 t sine of t minus 2t e to the 1/2 t cosine of t. Alright, sine, we've got a negative 2/5 plus 4 times 2/5 is going to be 8/5, so 6/5. E to the 1/2 t sine of t. Alright, that's looking pretty good. We're going to celebrate hard if we actually get the other one right. There's just terms all over the place, it's fine. Okay, so we get a negative 16 minus 4 is going to be a negative 20 over 5. Shoot. That's not what I wanted. That's going to be a 0. Nuts. Alright, where'd I mess up? The other one was alright. Almost. Alright. It's got to be something just with the cosines. It's supposed to be an 8/5, not a 0. Negative. Here, when I assume that this one was going to be the same in here, or in here. Hey, Cold Gold. Sorry. Yes, sure. Can post it here and or in pens. Pen centers. Doesn't mean I can necessarily answer, but you know, it's fine. If anybody has any questions, you can go to Penn Center's Discord. Penn Center is on Twitch TV/Penn Center, depending on what his schedule is. And also, these are all of the other 6 people, and I'm on there too, but the other 6 people who do math streaming fairly regularly. So, Dawn Does Math, Zach, or E to the 2I Pi, Penn Center, Ian Stuckey, myself, Danny Highway, and Dr. Gold will all do math streaming at some point. So follow all of the 7 of us if you really want to, find a good community of math people. We're probably going to be adding some more people eventually, as it stands. Right, this is the 7 of us that are kind of like starting the core group, and we're going to start expanding out as much as we can. Let G be a multiplicative group of non-zero complex numbers, and let C sub Z be the closure of the cyclic subgroup created by the non-zero complex number Z. Show that G without CZ is isomorphic. I'm not sure what the slash is in this particular case. Is isomorphic to one of G are real numbers, or S1 by S1 quotient. Okay, so it is just division. Oh man. I have not done abstract or complex in a very long time, so I think I'm gonna have to pass on this one. Yeah, okay. No, I was just thinking of it. It's not individual numbers or individual terms. It's a whole group. So yeah, never mind. Sorry. No, Penn Center is the one to really talk about for complex. Speaking of which, Penn Center is going to be doing a complex analysis class at some point in the somewhat near future. And by somewhat near, I mean like August. So we're going to be, I'm going to be participating in that. We're going to try to get everything all set up and have some good complex times. All right. Let's see. So yeah, sorry, Gold, not. Unfortunately, it's been too long since I've done any of that. Now I do have a massive pile of books next to me, so in theory I could at least look up what you're talking about. Doesn't mean I know anything about it, of course, but... Hello, good evening, or good morning, afternoon, wherever you are, and welcome to Phobos. Complex multiplication, Riemann convergence, explicit algebraic functions, graphical studies, differentiation. How's it going, Phobos Stream? Math GRE. Very nice. Yep, I actually have a Math GRE test Princeton review from... Oh, goodness, I don't even know when that is. Oh, is it just abstract algebra? Topology. Okay. Also a class I never took. Sorry. Lobster Chung, how's it going? Sorry, I had to get the contractors to make sure that they are coming on the right days and everything. Okay, so we said quotient group, normal subgroup, mathematical group obtained by aggregating similar elements of some larger group with an equivalence relation. Okay. Let G be the multiplicative group of the non-zero complex numbers So Kogol, do you want to use polar coordinates? I think that might be easier. Maybe, in theory. R sub I are not going to be equal to 0. Okay, CZ. Cyclic subgroup generated by C. I don't know what S is. Sure. 0.4 minus 0.8. Yep. Oh, is this one a plus? Is that the only problem? 16, 20. Oh, so those, no. 16 and 20 will make 36, will make that 32 over 5, so not that way. Right, negative 16, positive 20. It's not what it is. Is this one right here? Yeah, probably. This is a... sine. It's going to be minus. So this is the first one here, so that goes here. There's a minus out front of it. So that's fine. And then the... also true. Sometimes just say F it, throw the pen across the room. Point being, I like the linear algebra version better. I'm not doing it again. Sine has opposite signs. This times that makes it positive. So then the... right, so it should be positive then negative. So cosine times the 4. Yeah. I'm willing to write that one off. Anyway, so yeah. So walk me through it, I guess. What do you have so far? If C sub z is going to be closure of the cyclic subgroup, that should, in theory, mean that we have R equals 1 Because if r was anything other than 1, it would either shrink to 0 or grow infinitely. G be the multiplicative subgroup. Multiplicative group, non-zero complex numbers. Okay, here we go. Multiplicative group of complex numbers, set of complex numbers without 0 under the operation of multiplication. Complex multiplication must be well-defined, closed, associative, commutative. The identity is 1, and each element has an inverse. Okay, that I can do. So therefore, okay. So, not having any clue what this is actually talking about. Whee! Quotient group G/CZ see. Okay. Left coset space. Is a group where group operation is defined as a coset product A times CZ times B times CZ equals AB times CZ. Okay. So you're taking G, which is the multiplicative group. Alright, with complex multiplication, we have that it's closed, associative, and commutative. We don't need... yeah, okay, we do need commutative. Right? As long as this multiplication holds, then that should work for us. Like I said, I don't really know much about this particular setup. I didn't take topology, but in this, the left coset space has a definition that it's using for quotient group, which is talking specifically about multiplication all the way through. So you should be able to do something with this and say like, oh look, I can take the these constant factors and push them out, and just makes this thing. I'm not sure exactly, but you could probably make it so that your C sub z's are doing something with your like stuff up top here. Now, again, I'm using things that I know from undergrad, basically. So I may not have all the information. In fact, like, you know, practically none, but it's fine. See how it goes. Yeah, I think this works, because here you're talking about, like, R1 cis theta 1, this is going to be R2 cis theta 2. And when you multiply them together, right, and A times B are scalar multiplications, so they can just get knocked out to the front. This is going to be A times B times R1, R2 cis theta 1 plus theta 2. And this is within the appropriate space. Your multiplicative group definition is telling you that this is closed, so it has to be part of it. So then A times B times some member of CZ is going to be like so proven. Again, I don't know how to do it, but like this is a way. All right, I need to step out, so I think we're gonna try to just check and see who's alive. Ian Stuckey is on right now. So we're gonna go see them and send all the love that away. If y'all would stick around for this raid, that'd be really awesome. Whoa! Well, thank you. Oh, wait. I was looking at somebody else's chat. That was not mine. Never mind. Alright, I'm going to try to be back either tonight or tomorrow night. We'll see how things go. I only have a couple more days before all of my stuff gets taken away and shipped off to England. So, I am going to, however, still be using the favorite of everybody's, pen and paper, and see if we can't do some awesome mathy type stuff. So, see you all later. My name is Obi-Wan Pez. This is N Simplex Pachinko. We're going to send you over to Ian Stuckey. Here we go.